Welcome to Ask and Learn.
So we have two conducting spheres, which I'm going to draw like this. This is R1, and it has a charge Q1. And this is R2, and it has charge Q2. And we also know that the total charge is Q1 plus Q2. Now, the first part we want to show total energy associated with one sphere. So we know that the energy in general is going to be 1/2 CV squared, or we can substitute in Q over C for V. So this is going to be Q over C squared. This comes out to Q squared over 2C. Now we also know that the capacitance for conducting sphere is 4 pi epsilon naught times the radius of the sphere. So we can substitute that in right here, and we get Q squared over 2 times 4 pi epsilon naught R. Now I'll just rearrange this a little bit. So we have 1 over 4 pi epsilon naught times Q squared over 2R. And this first term here, 1 over 4 pi epsilon naught, is just the electric constant, Ke. So this is Ke times Q squared over 2R. And I guess the problem had this as a lowercase q, but it doesn't really matter. So that works. And now we want to find the total energy of the two spheres. So we'll just add the two up. We take U1 plus U2. It's going to be Ke times Q1 squared over 2R1 plus Ke times Q2 squared over 2R2. Now we want this all in terms of just Q1, and we know that the total charge is the sum of the two, so that means Q1 is going to be Q minus Q2, or actually I want that the other way around, so Q2 is Q minus Q1. So now I can substitute in for Q2. Q minus Q1 over 2R2. Now we have everything in terms of Q1, so that's the total energy. Now we want to differentiate this, so du with respect to Q1. Okay, so the first term, Q1 squared, derivative of that is going to be 2Q. So we have 2 times Ke times Q1 over 2R1. And now we have a minus Q here, so this is going to be minus 2 Ke times Q minus Q1 divided by 2R2, and we'll set this equal to 0 and solve for Q1. So this is going to be, the 2's cancel in each term, so we get Ke times Q1 over R1 minus Ke times Q minus Q1 over R2 equals 0. So Ke Q1 over R1 equals Ke times Q minus Q1 over R2. Now the constants are going to cancel. And now let me get all the Q1 terms on one side. So first I'll expand this out. And then we'll bring both Q1 terms, so Q1 over R1 plus Q1 over R2 equals Q over R2. Now I'll factor out the Q1. This is 1 over R1 plus 1 over R2 equals Q over R2. Now I'm going to divide by this, and when I divide by that, that's like taking the reciprocal, and the reciprocal of 1 over R1 plus 1 over R2 is the product divided by the sum, the same way you would get equivalent capacitance for capacitors in series. So this is going to be R1 times R2 divided by R1 plus R2 times Q over R2. So Q1 equals Q times R1 divided by R1 plus R2. Now, to figure out Q2 we know is Q minus Q1. So that's going to be Q minus QR1 over R1 plus R2. Now, let me try to get the same denominator, so I'll multiply by R1 plus R2 over R1 plus R2. This is minus QR1 over R1 plus R2. So this will be Q times R1 plus R2 and then minus an R1 divided by R1 plus R2, which is, well, the R1s cancel, so we get QR2 over R1 plus R2, so very similar to what we got for Q1. Now let's find the potential on each sphere. So the potential on the first sphere is going to be Ke times charge divided by the radius. And we know the charge is QR1 over R1 plus R2. So now divide that by R1. These cancel, and we get Ke times Q over R1 plus R2. Now the potential on the second sphere is going to be Ke times Q2 over R2, which is Ke times QR2 over R1 plus R2, and divide that by R2. So again, these cancel, and we're left with exactly the same thing. Ke times Q divided by R1 plus R2. And so we have exactly the same potential on either sphere. So the potential difference, I'll say from 1 to 2, is going to be 0 volts.